Now that we found out so much about these number lines and we have found out which kind of base we can choose, let's ask, well, do all these number lines agree, or are they each different in their own way? That is, suppose we have a number line that has subdivisions in A. So A squared, and so forth. But suppose we are not interested in A and its powers, but some other number B and its powers. So we're looking for a number B, and we've already found out that given a number, we can find its place on this number line. Now we can ask, well, where's B squared? Are we guaranteed that B squared will be exactly twice as far away from 1 as B? That would be nice, but it's not quite obvious. And then B third is 3 times as far apart, and so forth, and then all the negative powers. But that would be really, really nice. So that on the same number line, the succession of powers of A forms a regular number line, so to speak, but also any other succession of powers of some other base also is evenly spaced. That would be really nice. Well, there's an easy answer for this. Yes, it works. But why? Well, since we found B on this number line, that means that we have actually been able to write B as some power of A. Maybe only approximately with some rational number. Maybe we've done really well and found lots of decimal digits of x, and maybe in the limit x is irrational, but it doesn't matter. As long as we found the appropriate length on paper, actually the length on paper, let me also write this down, so to speak. So on paper, this is adding x. But then B squared, we've seen this is, well, it would be a to the x squared, that is a to the twice x. So starting from 1, on paper we go 2 lengths of x. And there you have it. B squared is just as far apart from B as B is from 1. And then it's no real surprise that this generalizes. So B to the third, B to the fourth, all these are evenly spaced. And then all the negative exponents as well. So exponential number lines agree. So essentially there's only one exponential number line. This has actually been used historically to great effect before we had electronic calculators. These kinds of exponential number lines were given as actual objects made out of wood and plastic to students to calculate powers of numbers or find inverse powers of numbers or all kinds of other operations that worked well with powers and roots. Now that we've seen that these stairs of powers actually work all on the same number line, we can now also justify one last rule of exponents, that is this one. And if x is a natural number, this was, well, it's really not much of a surprise because, well, if for example we say n copies of A in our old notation and then n copies of B is the same as n copies of AB. Just rearrange the factors. But actually, we now have a justification for this for any exponent x. Because what's happening? Let's say we take the product A times B. What is that? Well, we would have to take this arrow and join to it, which is times A, and join to it this arrow. So let's displace it and say, here it is. So this whole thing represents multiplication with AB. And we take the x power of it, that is, we scale it up even further. So maybe just some integer number of copies, but maybe it might be some other kind of scaling. So let's scale it up by a factor of x on paper. But what have we done? We have scaled up a juxtaposition of a and b, so it's quite natural to say, well, we could just as well have just scaled up a appropriately, scaled up b, so scale up a, and then scale up b, and putting them next to each other. That is a to the x times b to the x. For whatever value of x, integer or not, positive, negative, rational, irrational, it all makes sense if you think of it as continuous scalings on paper.